Right, okay, today our presentation is on Newton-Raphson's method. I'm not going to say what it is now, but I'm going to discuss some things which are going to give us the need to look at something which is called Newton-Raphson's method. Now, let's start this way. On this slide here, I've got two functions, e to the power minus x and the y to the y is equal to x. I suppose that these functions are known to everybody, and all of you must know these functions. What is true about these functions, what they have to do with this, what we're discussing today in Newton-Raphson's method. Notice that I think this graph, everybody remembers this is the graph of a function which runs like this. Exponential decay, and there it cuts at 1. Everybody must know that. It's our x-axis and the y-axis there. Is that fine, guys? Okay. And then this function is a function which bisects the right angle in the first quadrant and in the third quadrant. Now these angles there, they are equal. Now if we highlight this point here, I will put it as a dot so that it's visible to you. I think we can see there that the two functions e to the power minus x is equals to the function y is equal to x. Where does that take us to? This takes us to an equation of this nature, which is e to the power minus x equals to 0. What is special about this equation? I will explain to you what I think is special about this equation. Notice that this equation is not equation of the type 2x plus 1 equals to 0, where you can apply your algebraic operations and solve this for x. It's not even something like x squared plus 2x plus let's say maybe 1 equals to 0, where here you can use your quadratic formula to solve the equation, and there you can factorize and use your algebraic manipulation to solve this equation. This similarly you can solve this equation. This one, no. We don't even have a formula for solving this equation. Are we together? Okay. So then the picture which I've just drawn here is this picture here. So in other words, if we've got that function and that function, and we are searching for this point where the functions are equal, this point x here, let me just put it as x1. This point x1, which is under this point of intersection, will be the solution to the equation ex minus x equals to 0. But our problem is, how can we find that solution? We don't have a formula for that. Now, as I said before, this chapter is about applying differentiation and solving problems applying differentiation. So let's see how Newton's method uses differentiation to at least find an approximation to this solution. Because remember, in life, not everything we measure exact. Sometimes once we've got a good approximation of what we want to measure, we can work out with that value, then it's fine. Are we there? So now let's start it this way. There is a graph of a function. This function, I don't even care what is the expression for f of x. Let's just suppose it's an expression which is similar to the function which we get when we say f of x equals to e of x power minus 1 minus x. So when we set this equation to 0, we're solving that equation. As you can see, the graph tells us that the equation, this function, if we say f of x equals to 0, it will mean that the solution will sit somewhere there, because that's the way the level of the function is 0. Do you agree? Do you agree? Okay. So now let's engage this situation and see what can we come up with which can offer us a method to solve this equation and the similar equations. Now, just to tell you, what we're going to do here, we're not going to use a method like we use for quadratic formula where you just calculate and exact root. We're going to use what we call successive approximation. Now, we'll start by assuming a certain value to be a solution, but we assume that value to be a solution if we think that that value is close to the solution. Then we do successive approximation. We start with the initial approximation, we do the next approximation until we think we are close enough to the solution, then we get it. We'll see what I mean by that. Let's come to this slide. This is what we start. This is here, that's where we've got the exact solution. But it happens that we assume that x0 is close enough to that solution, we can work with it. We can take x0 as our initial approximation. So let's say there, x0, initial approximation. So that is our initial approximation x0. Then notice that at x0, just above x0, I've drawn a tangent line, the red line there. That's the tangent line. I'll just call it T. That's the tangent line. So this is a point of tangency. Notice that the points of tangents there is on the red line, the tangent line, and is on the green graph. Do you agree with that? So then if we look at the graph, we'll say that point here is x0, comma, f at x0, the value of the function at x0. Whether we're talking about the line or we're talking about the green curve, is the same thing. I would like to know that, do you agree with that? That this, we can call this point x0, comma, f of x0. Okay. Now, if that is the tangent line, we can see that that tangent line crosses the 0, the x-axis there. Now the tangent line is got its 0 there. Let's call that x1. Let's call that x1. Now, the coordinates of this point here, I hope you can see that the coordinates of these points are x1, comma, can you complete the gap? 0. Good. Now, if we go back to differentiation, I think you will notice that if we now think of calculating the derivative at x0, now is f prime at x0, we need this point and that point. And that derivative actually will be the gradient of the tangent line, and there will be the slope of the green curve there. Are we together? The instantaneous slope of the green curve there. Remember, the slope of the tangent line and the slope of the curve at the point of the tangent is the same. Now the slope of the tangent line is equal to the slope of the curve where? Exactly at the tangent line. So that slope is equal to f at x0 minus 0 over x0 minus x1. Everybody must, I hope everybody understand that that is the usual calculation of a gradient m for a straight line. But that gradient now, it serves as a gradient of the straight line t, and there's a gradient of the curve there. That's what you should understand from differentiation. Now, if we play around with this, I think you will see that this is take us to x0 minus x1. And then multiply by f prime at x0, and that is equals to the function f of x0. If I divide both sides by f prime, we are going to get x0 minus x1 equals to f what? F, oh sorry, f not f prime. Is equal to f of x divided by f prime at x0. Sorry, here is x0, not f of x only. Are we together? Okay. That is simple algebra. I'm just manipulating that algebraically. Then next thing here, I can subtract on both sides x0. Can subtract on both sides x0. I'm going to be left with minus x1 equals to minus x0 plus f of x0 over f prime at x0. Please guys, make sure that you understand what I'm doing, because if you get lost, you get frustrated, the next thing, the example is not going to make sense, everything is not going to make sense. That's bad. Is everybody there? Okay? Then what I actually want to do here, I want to make x1 subject to the formula. So but I've got minus x1 here. So I'm going to multiply everything by minus 1. So if I multiply everything by minus 1, says x1 is equals to x0 minus f at x0 over f prime at x0. I think we should clap our hands for ourselves there. What is this thing told us here? Now, here at this stage here, we're being told that we could have calculated x0 there without even drawing the tangent line using this formula. That's what it said. That's what the algebra has given us. It says this x0, the point of intersection of the tangent line, can be calculated this way. So now, if we follow up exactly the same process, what's going to happen? We're going to have x2 here, x1 here, and now draw another tangent line above x1, and then the tangent line is there. But notice one thing, our initial approximation was this one, then from that one we managed to get x1. Notice that x1 is closer to the 0. So please notice that when we started with our initial approximation, x0 was here. Now when we get x1, look, x1 is closer to the 0. Now if we do the same process we did there, we will get x2 somewhere here, which is even closer to the 0. So I think there you must get this sense of successive approximation. You get one approximation, then you do that calculation, you get a better approximation, you do that calculation, you get a better approximation, until you decide that no, I've got enough accuracy for my purposes, then you can stop. All together? Okay. So let's do exactly the same thing. So what I'm going to do here, what I'm going to do there, we're going to say now, the point here is x1, f at x1. That's the point. There. Then this point here, like before, is going to be x coordinate x2, comma, x0. And then we do exactly the same thing. We now calculate the derivative of the function x1 equals to f at x1 minus 0 over x1 minus x2. Agreed? Then we play around with our algebra again. Then we're going to have f prime at x1 brackets x1 minus x2 equals to f at x1. Doing exactly the same thing we did before, dividing both sides by the derivative, we get x1 minus x2 equals to f at x1 divided by f prime at x1. Actually, what we don't know, you know x1 because we've calculated with the formula we've seen before. So what we don't know actually is x2. So we need to leave x2 as the subject of the formula. So subtracting x1 both sides, we get minus x2 equals to minus x1 plus this ratio f of x1 over f prime of x1. Remember, we need the subject formula to be x2. So multiply both sides by the minus sign, then we get x2 is equal to x1 minus this ratio, which is f at x1 over f at f prime, at x1. Now, if you follow that process and look at that pattern and go back to what we saw here, if you saw we see what we saw here, this, and look at our final results here, that is so almost suggests that, look at this, 2 here is actually 1 plus 1, and here we got 1, 1, 1. So the number which is used there and there and there is 1 after, the number which is used there and there and there, you add 1 to it, you get the next approximation, which sort of tells us that if we wanted to go up to n plus 1, then this would look like x, look at this, 2 minus 1, 1. This look like n minus 1, n. And then minus f of x n over f prime at xn. And that is what we call Newton's Raphson formula for getting these approximate zeros of these functions we don't have formula for finding their zeros. So that's the result which you want there. This is what I've been trying to, I didn't want to give it to you, then you think I take it from my pocket. It's like that. I just want to show you that this is something which is thought out logically following what we know, in this case applying differentiation. Is that good? Is that fine? Okay, so there is the formula. There is the formula. I've already given to you there. That's the formula. You are going to be given, most cases when you are asked to solve these exercises, you are going to be given this formula to solve. Now, what I want to do, I want to discuss with you the very, very first example I started with of that equation, E minus X minus what? X equals to 0, and see whether we can find an approximate 0 for this type of equation. Are we together? Okay. Now, the question would be, how do we get our initial approximation x0? What is our x0? Our x0, if it's not given to you, you have to use your analytic skills, your knowledge of graphs or functions to determine it, or to just come up with an approximation. Check how I'm doing it here. The way I'm doing it here, I'm trying to show you, maybe to just give you an idea of how I'm thinking to get this 0 altogether. So that the day when somewhere outside the industry you get a similar problem, you can try to think along the same lines to get an initial approximation altogether. If you get a good initial approximation, you'll work less. If you get a bad one, or something which is very, very far from 0, you'll work more. So you must make sure that your analysis, your kind of analytic skills are very sharp to see that, no, this is bad, yes, this is a bad initial approximation. So let me see what I'm going to do here. Let's check this. In this function, I've got two functions involved here. Here, I've got y is equal to e to the power of minus x. I drew them already before. And there, I'm going to y is equals to x. So let me try to sketch these functions. I've already sketched them, but I want to go to the initial slide there. This first function will go like this. It's a decay. And you know that this is 1. If we choose exactly the same scale, 1, I think 1 here will be somewhere there. So if I draw the straight line will go this way. And then the point of intersection is somewhere there. And then the value of x there is just below here, perpendicularly below there. That's the 0 we're looking for there. I'll just say xr. I'll call this one xr. Now the x, which is the root of the equation. Are we together, guys? Yeah, call that xr, which is the root of the equation. So now, I'm now using my analytic skills. Look at this. I can see that this number is less than 1. And the way the graph is drawn there is a rough sketch, but it sort of seems to be almost close to half. Maybe 0.6, maybe 0.5, maybe 0.7, I don't know. But it looks like close to the half. Do you see to that? If you see that, then let's assume that our x0 is equals to 0.5. I'm not saying that's the 0, but I'm saying my first approximation, let's make it 0.5. Are we together, guys? Okay. Then, as it is important to work organized, this is what I put on the table. This is what I did here. I drew this. If you look at the formula needs xn's from 0, 1, 2, 3, up to I don't know. It needs the function itself. In this case, the function is this one. Let's write it down. The function is f of x equals to, the function gives us this equation is f of x equals to e to the power minus x minus e. Who can give me this derivative? The derivative, what is the derivative? What's the derivative? Can I hear somebody talking to me? Once. Minus e, that, yes, minus 1. All together. So there we said our initial approximation x0 is equals to 0.5. Please guys, I hope lock your system with this explanation so you can get everything what is happening here and you can be able to repeat it on your own. Now this x0 is an xn where n is 0. So I'm going to write here 0.5. Now listen to this explanation. The exercise says, choose the suitable initial approximation and give your answer to correct to 4 decimal places. First equation says, use Newton-Raphson's method to determine the root of this equation. Then it says, choose a suitable initial approximation and give your answer correct to 2 decimal places. No, sorry, 4 decimal places. Let me tell you something if you are not aware of this. When you talk of decimal places, each time you take a number, maybe with 10 decimal places, you round it off to 9. You are introducing an error to that quantity. If you round it off to 5 decimal places, you are even accumulating a big error to that quantity. So now, please, when you are asked to work to give your answer to 4 decimal places, please do your calculations with at least, that's my recommendation, with at least 6 decimal places. Did you hear what I said? If you are required to give an answer to 4 decimal places, I recommend that you work all your workings, all your calculations, please work with your decimal numbers to 6 decimal places. Then I'll show you later how to stop the process of this calculation. So for that, now I'm going to write this as 5,0, 0, 0, 0, 0, 0. How many decimal places are there? 1, 2, 3, 4, 5, 6, 7. Is that right or wrong? Is it right or wrong? It's fine, is it? I said at least the minimum you can use is 6. I'm using 7, I'm fine. All together? Okay. So now let's do that. Let's evaluate the function there. In other words, just come to this function and say e to the power minus 0.5 minus 0, 5. That is only scientific calculator. Please use your scientific calculator. Give me that value. I'll put it there. Please make sure that your fingers are a bit swift. Be fast in calculations. Now, when I write the number, if one person gives the number there, I'm going to write it there for all of you to observe it. You must critique it. If it's wrong, you must say it doesn't agree with you. So when you get a number there, you must make sure it's a correct number. Otherwise, we're going to spend the whole day here using wrong numbers and not get to where we want. Altogether, everybody must calculate the number. Who has got the number? Yes? Minus 1 comma minus 1 comma 1 so the next person is talking. What are you saying? 0.1065 3062467 5. Then just get to the derivative now. Do exactly the same thing. To be e to the power minus e, minus e to the power 0.5 minus 1. What is that? Come again? Minus 1 comma 6 0 6 5 3 0. Nothing else? 7 6 6. Let's put it as 7. Then let's calculate this one. How do you calculate this one? Using the formula, isn't it? It should be x0 minus the ratio of these two, isn't it? Remember? Yes or no? So it should be calculating this one should be x0, f of x0 over f prime of x0. Here is f prime of x0, here is f x0, then here is x0. So do this calculation, please, and give me the answer. Obviously, you see there's a minus sign here. If you divide with the minus sign there, it's going to be a positive, isn't it? So whatever you get here dividing, you must add it to 0.5. Yes, my sister, can you give me the answer? Hello, this brown lady in front of me. You. You're still calculating. Your fingers are still slow. Yellow, here? 0.566 Come again? I don't hear what you're saying. 66111. Can you speak up and tell me what's the number? 0.566. Come again? 31. 09. what is that? That should be x0 plus 1, which is x1. So we take this number. Please understand what I'm saying here. When you get here, this is not x0, it's x0 plus 1, which becomes x1. Then that's the number we're going to start with here. 0, 5, 6, 6, 3, 1, 0, 9. Do you agree? Do you agree? Did you check your value? You still get the same answer. So just double check if it's something like that. Okay. Okay, let's come to this one now. Let's use this one now. Come to this one. Please, can you do your calculations faster? Listen, guys, this is not time to write. Can you calculate? Then I'll give you a chance to write this thing, or you can repeat this thing for yourself, as you know what, long as you know what you're supposed to do. Hello, can you please do the calculation? You do this value, and you do that value, we put them there. Where's got the first value? Engineering students who cannot use calculator. Just two functions, e to the power this minus this. One. I doubt whether there's a number called 1 there. I don't think you can get a number which is 1. Who's getting 1 also? 0, 0, 0, 1, 3, 0, 0, 4, 6 or 7? 6, 7. Okay, then let's get it here. Come again. Minus 1, 1, 3, 3, 9, 2, 6, 4. The fact that I'm writing this number, I'm not saying I'm accepting it. I'm writing it so you can see it and see if you agree with it or don't agree with it. If you don't agree, people must change that number. You must critique that. Is it correct? Is it correct? What is the number? No, don't be too fast. Say it minus 1, 5, 6, 3, 5, 6, 7, 6. 5, 6, 7, 6, 1, 5, 6, 6 or 7 there then? 6. Okay, let's calculate this one. I said this is time for calculating, it's not time for evaluating. Give me the button. 0,567 1 4 3. Are we together? Now listen to me carefully. If I were asked to get this number to 2 decimal places, I would stop. Why? Because to 2 decimal places is 5, 6, rounded off 7. 2 decimal places, 5, 6, rounded off 7. You understand what I'm saying? I would stop if I were asked to what? To stop for 2 decimal places. Are we together? So I've got 2 patterns there which all lead me to the same 2 decimal place. So which means for 4 decimal places I should also have 2 patterns, one after the other, which both lead to for same kind of 4 decimal places. Are we together? So we are not yet ready to stop here, because if we go to 4, 1 up to 4 there, this rounds off to 5, 6, 3. But this rounds off to 5, 7, 3. We cannot stop for 4. Do you understand what I'm saying? So that is how you stop. So now, this is our x what? 2. Then we take this number, put it there. 5, 6, 7, 1, 4, 3. Is that right? I don't like this one because it's exactly to 6. There's no other decimal place here. Yes? So sorry, just hold on, let me answer this question first. 2 here. Okay? And then 3, 2. Right, let's have the next value for f of x2. What are you saying? 0, 6 zeros, 2, 4, 6 zeros there. Then 1, after 1, 4. Let's have it like that. This is why I'm insisting that we go to 7, because if you do that at 6 zeros, you just get a 0, then you cannot maybe make a good sense of what's going to come next. That's right. Now let's calculate the value. Let's calculate the value. Is that number correct? Okay. Let's calculate this one. Yes, my brother. Can you know? Minus 1.567 1 4 3 2 4 6 and 3 again. Okay. Right. Let's calculate this one. A bit faster. Who wants to give me the answer? 0.5671 4 3 2 433 433. Okay. Now, listen, my friend. How do you stop now? We are targeting 4 decimal places. I underline the 4 decimal places there. Up to that 1. And there. Up to that 1. If I round off this one 4 decimal places, I get 5, 6, 7, 1. If I round off this one, 5, 6, 7, 1. So which means I will stop my calculation here. Because if you try to continue, but what I'm going to continue with, was you continue this value there, it's going to come back and give you the same thing altogether. So it becomes redundant to continue. So before I said, if you were to stop at 2 decimal places, you would underline 2 decimal places there and underline 2 decimal places there. This number to 2 decimal places, it rounds up to 0.57. And this number would round up to 0.57. Then I would stop there if it was 2. For 4, I will stop here because you have seen what I've explained altogether. So you don't just stop. You stop when you see like 2 successive calculations there, rounding you off to the same number. Then you stop. Then you know that you have given. Then now what are we going to say now? We are going to now say, therefore, our root x, xr, is equals to 0,567 1, then you must write there, correct to 4 decimal places. I don't have space there to write, but you must write there, correct to 4 decimal places. That's to say that is an approximation with that kind of accuracy. All together. So I hope this example is clear and everyone can be able to repeat a similar problem with using the same formula. Otherwise, I'd like to say there, thank you for listening. My name is Charles Wasfani Msipa.